Yeah, so we talked about base quantities, and base quantities are basically these 7 that we talked about. And they're basically the ones that scientists have just agreed on that, all right, we need to standardize them. And then we will compare everything to these because these are the base. All right. So if you look at them, it's quite hard to represent one in terms of another. So mass is mass. It will be a difficult task to explain mass in terms of length or in terms of time or any of time in terms of length or something like that. So while we can draw some parallels in them, they are very different from each other. And that is probably one factor that they said that, all right, we have 7 of these and we will try to explain everything else based on measurements that we do for these things. And now the first 3, we are going to talk more about them. For now, I'm going to talk about just length and time. We have already talked about how we can measure time. We don't really measure time, we measure time interval. So we use a starting point and ending point. So if it is time, you probably will start with a stopwatch at 0, or you will look at the clock and you'll be like, okay, what time it is now? And then you figure out the time later on, and then you subtract them to figure out the time interval. It's the same thing with length. You start with 0 if you want to avoid any 0 error, or you want to make sure that your starting point is perfectly synced. And after that, you move on to your, so after you have your the length that you want to measure, you subtract the starting point from there. So if you're using a scale and it started at 2, you'll subtract 2 from it so that your value gives you the actual value that you have. Of course, you can improve how precise or how accurate your value is by improving your technique and your instruments. So both of them are important. Technique, especially for accuracy, and instruments, especially for precision. Of course, these things are interconnected. So we'll talk about length and time for now. And the study of length and time, how they're connected to each other, that we call kinematics. Kinematics means that study of movement. So we're going to start with what exactly are we moving on. So we are moving and we are traveling and we are covering some distance, right? So that's the first term that we have, distance. What exactly is the distance? You have a point A, which might be your starting point, and you have a point B, which might be your ending point. So this might be one path that you take. So how long is this path in terms of length? That is the distance. So it is the length between 2 points. That's simple. That's what distance is. But there's the thing, the length is not fixed. So if you're going from A to B, you might want to take a longer route like this. Maybe that route is safer, or maybe you're getting uh, a bus that only goes through that route, or it could also be a very windy or dangerous or different path that goes like this. Maybe the point B is not very accessible, so you have to go on an adventure to reach there. And obviously, you can go around the world and get back to B. It's totally your choice. You can have an intergalactic journey and then come back to B. That will still be a distance between A and B. Of course, that distance might not be very practical, but still, it is some distance between them. So we can say that the distance between any 2 points can virtually be infinite. Like you can have the 2 points that may have, let's suppose, one point A and one point B that are really close to each other, or maybe they are so far apart that you have to travel through, I don't know, the whole universe to get back to B. So again, it's totally your choice of path that determines the distance. But the thing is, it's not the most efficient choice of path if you're going to choose a longer route over a shorter route. So in nature, many things travel between one point and another. These could be electric fields, these could be magnetic fields, this could be waves, these could be sound, this could be many other things. And all of them try to optimize their path. And though that optimization obviously comes from which is the shortest path, and that is obviously the most optimized route. So the shortest length that we have, that's a specific length that we call displacement. And displacement is important because it tells us the shortest, most optimized, least resource using path between 2 points as far as many different phenomena are concerned. Okay, so that can be light, electricity, sound, or many other things moving from one point to another, and they will preferably choose the shortest path or shortest available path. So shortest path or shortest distance, shortest length between 2 points. But there's a difference. It's not always between 2 points. It's now from one point to another. So there's also the idea of a starting point and the ending point. So obviously there's a direction involved. So you can go from A to B and come back from B to A. Your distance might be the same because you have chosen the same path, but because your direction has changed, your displacement is going to be different. And that is the main point here, that displacement is a vector, distance is a scalar. So distance does not have a direction. So by the time you give distance a direction, if you're going to do that, then it becomes a displacement. So what's displacement? Displacement is nothing but distance with a direction. So here's the thing. Let's suppose I define my direction in one direction and I call this, okay, this is my vector D. And this is just a direction. And I'm like, okay, I'm going to go 5 steps in this direction, same direction. So my total distance, and let me call that S, is going to be 5 because that's the magnitude in the direction of D. And I'm putting an arrow here to show that this is a vector, and that makes the whole thing a vector. Okay, so in physics O levels, we prefer the term D with an arrow to represent a vector. In A levels, we prefer S for other things because D is already occupied with derivatives. So S for displacement. But the difference is that S or D doesn't matter. It's only that you have a magnitude and you have a direction. So obviously this direction, if you're going to go opposite, and if you're going 5 steps opposite, you have to show that you're going opposite. So for that, we say that this is minus 5D. So the idea of plus and minus is simply to tell us that in plus is in one direction and minus is in one direction. Obviously, you have complete freedom to decide what's positive and what's negative. So again, this is a matter of choice, it's a matter of preference. So you can define your positive in any question that you solve in any way you want. So for example, you're solving a question, you're like, okay, up is positive, so sure, down will be negative. So anywhere in that question you choose a vector going down, that will be negative, and a vector going up will be positive. Another student chooses that, all right, my vector going down is negative and vector going up is my vector going down is positive and vector going up is negative. So I'm going to choose that, and they will mathematically be absolutely correct. So the problem will arise when one of those students tries to talk to another student, right? Because one will be talking, okay, I went 5 steps positive, and the other one will like, no, 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 you went 5 steps negative. And it can cause confusion, and that confusion can have consequences. So to avoid that, people usually agree on that what is positive and what is negative. And that's what we are going to do here. We are going to define positive in a way that many scientists have done for the last 2.5 centuries. So we are going to use this thing. This is called a two-dimensional Cartesian plane, named after Descartes, who was a Frenchman and a very famous philosopher. So this is Cartesian plane. It has X and Y. X is simply horizontal and Y is just vertical. And we are going to say that, all right, X is positive in one direction. If you're going right, it's positive. And if you're going up, it's positive. And if you're going down, it's negative. And if you're going left, it's negative. So X and Y are perpendicular, or we also have a word orthogonal. Again, not required in O levels. So these are perpendicular to each other. They don't really affect one another, and they can be considered independent of each other. So if I'm going from this point to this point, what have I done? I have to go a certain distance to the right and a certain distance up to figure out my actual starting and ending points. So this is basically called triangular law of addition, or in simple words, head to tail rule. What you're doing is you're taking two vectors and you're joining them one after another. So you start with one vector, wherever it ends, you put the other one, wherever that ends, you put the next one, wherever that ends, you get the idea. So you keep on doing that, and you're starting and ending point, you join them, and that is what you call resultant vector. So let's suppose I have multiple vectors. I have this vector, I have this vector, I have this vector, I have this vector, I have this vector. And I want to figure out, okay, I am applying all these vectors and I want to add them. So let's do it. So I'm going to take this one, place it here. Okay. Uh, Head to tail rule, triangular law of addition, vector addition. Okay, now I'm going to take this one. Interestingly, it doesn't matter what order you choose them in. So I'm going to place it exactly where the other one is ending. Then I'm taking this one. I'm going to place it exactly where this one is ending. Then I'm going to take this one, point it where this one is ending, a little down, thoda sa. Yeah. And then I'm going to take this one and I'm going to put this one here. All right. So I had 5 vectors and I have joined them one after another in the same procedure. And now my resultant is, this was my starting point, right? And this is my final ending point. So this is my resultant of these 5 vectors. So you're just adding all of them up. And so you're ending here. All right. So that's vector addition. You can do it that way. If you have just 2 vectors, then what do you do then? So if you have just 2 vectors, then it gets even easier. So let's suppose I have 2 vectors that are at the starting at the same point. So I'm starting here and another vector is starting here. So what I'm going to do is I'm going to copy this vector and place it here. So I'm going to take this vector, this whole thing, and I'm going to make a copy of this. So sorry. Yeah, I'm going to make a copy of this, place it here. Secondly, I'm going to select this one. Okay. And I'm going to make a copy of that as well and place it here. Now you notice that there is one point at which both of them are starting and there's one point at which both of them are ending. So what I'm going to do is I'm going to connect these points from this to that, and now that is my resultant. And I'm going to represent that with R. So 2 ways of adding vectors. One is that you take every vector that you have, you join its tail with the other's head. So head to tail rule. So one head, next tail, then one head, next tail. Eventually, you have arranged all of them in an order. Doesn't matter what order it is. So your very first starting point and your last ending point, you join them together and you have reached a resultant, the final vector addition, the vector result that you have. The other option is you have 2 vectors. So it only works for 2 vectors or maybe 3 vectors in 3-dimensional plane. But for now, we'll just keep it to 2 vectors. So if you have 2 vectors and they're all starting at the same point, that's important. So if they're both starting at the same point, then what you do is you make copies of them, you place them like this, and now you have a parallelogram. And this one is called Parallelogram Rule. So now it is Parallelogram Rule of Addition. Again, this is just an extension of, in fact, a simplification of the head to tail rule. Head to tail. So head to tail is that you take a vector, you join them together like that, and parallelogram is that you just make 2 vectors and you add them. Obviously, you will be required to make some measurements. So far, we have only drawn them. We haven't made any measurements. So I will need to measure the length of this vector. So I don't really have a scale that I can use here. I don't know if there's a tool here that I can use. I'll check about it. Maybe we can later on. So for now, we'll take a ruler or scale and measure the length from here all the way to here. And we'll be like, okay, this is the vector and this is the direction. And you will measure this direction with protractor. Okay. So obviously you need to avoid parallax error when you're doing that. You need to look at it head on so that you can make a very accurate measurement. Okay. Precision obviously depends on what kind of a protractor are you using, but accuracy depends on your technique here. Same for this vector. You will probably draw a horizontal line here and take its angle. And then you'll be like, okay, this is the length. And you have figured out the length and the angle. And that is what we need. All right, so that is how you add vectors. So displacement, I've told you, is shortest distance from one point to another. And because it's a vector, you need to know how to add displacements like this. Displacement, like other vector quantities, can be negative, but distance cannot be negative. That is a very, very important difference between distance and displacement. So here's the thing. Let's suppose you are traveling on a car and this is your home. Okay. So last time I took drawing was probably in KG. So you have a car here and you're traveling in it from you left home, went all the way, maybe you went 2 kilometers and then you realize, oh, wait a minute, I dropped something back at home. And you come back maybe half a kilometer and you're like, no, wait a minute, I dropped it on the road. So you stop and you pick it up. So my question is, what is the distance that you've traveled? Yes, exactly. You have traveled 2.5 kilometers. Now your mom calls you from home and she's like, you left home quite a while ago. Where are you? What will you say? How far are you from your home? Are you 2.5 kilometers away?
1.5.
You're 1.5 kilometers away, right? So that is how far you are from this point in this direction. That's 1.5 kilometers. But how much have you traveled? You have actually traveled in this path. So going back in a path reduces the displacement because you're going exactly in the opposite direction. You're getting closer to your starting value. And so if you were to go back all the way to your home, you're like, no, that was a mistake. I actually left it at home. Then you have traveled 4 kilometers in distance, but 0 in displacement because you're back to where you were. So overall, you have probably achieved nothing and you're late. So displacement and distance are different in just this sense. If I were to graph it, and physicists, they love graphs. So if I were to graph this thing, so I'm calling this distance here and the unit is meter. Notice how I write it, distance / meters. And I'm not using the full word, I'm just using the symbol. And time, I'm using small t and second. So time and second. Notice second is not SEC, it is just S. And any other way of writing second is also not acceptable, just S. So here's how you're going. You went from here to 2 kilometers. Maybe you took 10 minutes and then another 2 kilometers. So you took overall maybe 20 minutes or 20 seconds, sorry. So that is a distance graph. You're going, you're increasing the distance. This is where you thought that, oh, I should return, and then you came back. But what is the displacement of the same journey? And remember, displacement is always from the starting point, okay? So I'm going to call this d with a vector so that I know it's a vector quantity. Time is again a scalar, seconds. So for the first 10 seconds, you went to 2, all right? So this is what you were doing. So your displacement from your home is 2 kilometers now. Oh, sorry, 2 meters. I'll change it to kilometers just for consistency. And now, after that, what are you doing? You're coming back. And at 20 seconds, you're back at home. So your displacement is down to 0. Because displacement time graph will tell you at any point where exactly you are from your home. But distance time graph will only accumulate everything, every meter or kilometer that you've traveled. So same journey, different distances and displacement. And that is a graph that we need to understand. Okay, now you do the same journey, but now what you're doing is you continue and your mom's like, okay, I need you to run some errands, so go in this direction. So you're going there 1 kilometer away, and then you coming back by picking something up. So let's continue this graph for your journey. So I'm going to copy all of this, place it here. All right. So you traveled, as far as distance is concerned, now you've traveled 4 kilometers earlier on, so you're back home. 1 kilometer further, so 1 kilometer further, that is 5 in total. And then another one to come back home, so that is 6. So probably all in all, you have traveled 30 for 30 seconds. What about displacement? Your displacement is quite different. What you've done is that for right now over here, you are traveling in the positive direction, but suddenly when you're back at home, you're traveling in the negative direction, right? Over here. So your direction has changed. So now when your displacement is 0, you've started to go back in the opposite direction. So aapne 1 kilometer in the opposite direction travel karna. This is -1 because it's in the opposite direction. And then you come back home when the time is 30 seconds. Got it? So overall, how much distance have you traveled? 6. How much displacement have you traveled? 0. And do you get it? Everybody? Any questions on that? That how displacement and distance are related? Distance just keeps on adding. Displacement is adding and subtracting based on where you're headed. Okay? Any questions for this? Great. So can you draw a graph of this thing that you are? So now there's somebody, you have a toy car, and now that toy car is moving on this path. Okay, so that's a hill, goes like that. You leave the car here, whatever that is. So it travels. Okay. The distance traveled up till this point is, I think the total distance of the track is up till this point is 12, up till this point it is 16, and up till this point it's 20. Okay. Now go on and try to draw a distance time graph for this from the starting point, like from here. This is a draw the distance time graph for this thing. And forget about whether it's going to be a standard straight line or a curve or whatever. Just draw the path or distance time graph. Any success? Anybody who's drawn it? You can WhatsApp the picture of your graph, or you can just turn your camera on and show it to me. So what's happening here is that there is some change in the way this thing is traveling at 16, and then obviously it continues on to go on to 20. There isn't any information about the time it took for this to travel. People, you need to take part in this. Yeah, so this problem was actually ill-defined. Why was it ill-defined? There was not enough information available. There was absolutely no idea of how this thing is moving, whether it started at some high speed, whether it started at some zero speed. We don't really know about that. And we haven't really talked about speed so far. And then is this going to change its path and slow down or those kind of things? There is no problem in that. How much time it took, that's also not mentioned. So we are just making stuff up. Ill-defined problems are important because they give us, they make us ask more questions. So I will be giving you ill-defined problems, and you will need to ask questions to get that clarity so that you can do the right thing. Now, here's the thing. Let's discuss these. So what do these graphs on their own tell us? So first of all, this graph is telling me that this is certainly traveling, and it's traveling from 0. So the distance is certainly from 0. So obviously that is 0 because it started at A. And it keeps on going. And then for some reason, the line is steeper here, and then it's not that steep, and then it's steep again. So there might be some physical manifestation of this steepness of the line. Similarly, over here, while it's the same way over here, that up till this point, it's a straight line, and then it starts to go in a curve. But this is very interesting because there's a dip here, which shows that now the distance traveled has decreased. And that is quite difficult to do. Once you've traveled a distance, you cannot undo it. You can decrease the displacement, but you can't really decrease the distance that you've traveled. Every step that you take is going to add up to the total steps that you've taken, right? So that means distance time graph will never come down. That's not possible in it. It will only go up and up, or it can just stay where it is. It cannot go down. And similarly over here, there is some degree of change available happening here, and then suddenly this thing. So we need to find a way to compare these curves. Like, what does this steepness of the graph mean? And it does mean a very important thing. It means speed. And this speed is basically how fast or slow you are traveling. And what exactly is this? It is simply the rate of change of distance. So rate of change of distance simply means how fast or slow you're going. And this can be defined, if you were to define it mathematically, it will simply mean how much you have changed the distance. So change in distance, this triangle means distance. Oh, sorry, this triangle means change. So the change in distance compared to the change in time. All right, so this guy went from 0 to 5 and traveled 12 kilometers. So on the y-axis, the change is 12. On the x-axis, the change is 5. So how fast is this guy going? Oh, this is going 12 kilometers in 12 meters in 5 seconds. So 12 meters in 5 seconds. So that is what? 2.4 meters in 1 second. And that is standard. That is something that we try to do, that we try to compare everything to unit in the denominator. So that is what the speed is, 2.4 meters per second. That means that every second it's moving 2.4 meters, or it's moving 12 meters in 5 seconds. They're both the same. The rate is the same. And this we call speed, and that will represent with a V. No arrow here. Uh, so what about this part? So over here, it started at 12 and it ended at 16, and it took 20 seconds for it. Did it? No, actually, it took 5. It started at 5 and ended at 20. So the total time taken was 15. What have I done? I've subtracted the time. And total distance traveled was not 16. It was 16 minus 12. It was 4. So all that I've done is I made a triangle. And the length of this triangle in this side is telling me the time interval. And the length of this distance is telling me the distance that it has traveled in the interval. So that is 4. So for this part, its gradient or its rate of change is going to be 4 meters in 15 seconds. Clearly, that is so much slower than 12 meters in 5 seconds, right? It has taken triple the time and only done 1/3 of the distance, right? So that simply tells me that this is slower. So what does that mean? How do you relate the graph to speed? So less steep graph means slow, more steep graph means fast. Why? Because more steep graphs cover higher values in y-axis compared to the x-axis, and less steep graphs cover less values in the y-axis than the x-axis. All right, so that's it. That is speed. And how is it related to the graphs? The steeper the value, the higher the speed. All right. But what about displacement? Let's try to draw a graph of the displacement of this thing from, I don't know, maybe this point, B. So I'll try to do that. So as far as B is concerned, this point, let me try to. Okay. So you can all see it, right? So as far as B is concerned, this point when it started out is at minus 12 meters away from it. So my distance in meters and time in seconds. So when it started from B, this thing is at minus 12. And then it comes towards it and ultimately it reaches B. So when it reaches B, the displacement is 0. Right? Do you see that? The displacement from B was negative in the starting. Why? Because we're measuring at B, so it is in the opposite direction coming towards us. Now it's going away from us if you're standing at B. And how far has it gone away? 4 meters when it reached this hilltop. So it has traveled 4 meters here. And then it went 4 again. So that is 4 more. So the displacement time graph is very, very different from the distance time graph. There are 3 portions of it, just like there were 3 portions in all of the displacement time graphs that we got. And what's the total displacement that this thing has traveled? 8 from B again. Okay, so this is displacement from B. It's a vector. And you're counting your distance from your starting point. Okay, so you can see that the speeds, I haven't really paid much attention to speed here, but the speed is still relevant, except now we are going to take gradient of this displacement time graph. And now the gradient can be negative because displacement come back. This thing can suddenly turn around and come back to B. And in that case, displacement will start to go down. But distance can never go down. So that means we need to have some differences in the gradient of the displacement time graph and the velocity time graph. And that, in the speed time graph, we call it velocity. The distance and displacement are slightly different in the sense that displacement can be negative or it can be going down, but distance always goes from 0 all the way up. So velocity is going to be the same thing, rate of change of displacement. And this can be negative, which means this velocity itself is a vector because it can be negative, right? So the way we define is still the same. The change in displacement, but a vector, compared to change in time, and that is velocity, which is itself a vector because it can be negative, right? Okay, so that is the distance time graph and displacement time graph and how you draw it. So the faster things have more steep lines, the slower things have less steep lines. So far we're just talking about velocities that are changing and are constant for the time that they have. Tomorrow we'll talk about velocities that are more fluid, that change slowly over time, and also the speeds that change slowly over time. Okay. So any questions in distance time, displacement time, or the graphs that you have? So the task for today is think of a journey of anything. It could be a bird flying around. It could be you going for a walk. It could be a car that just passed through your house or anything in front of the house, I mean. So you just have to take any object, it could be the sun or the earth or anything, and draw its distance time graph and displacement time graph for a certain interval that you choose. All right. Thank you so much.